I'm going to try and talk a little bit about RTOS in an embedded environment and kind of a little bit about what it is. I've got a video I'm going to try to show that will do a much better job of talking about what an RTOS is and why you might want to use it. It's about 11 minutes long. I have a collection of the documents I'm going to walk through, kind of notes to myself. I've posted that out onto chat as well, and that will be available to whoever wants to go down this road. So this is my document that I have out on GitHub. And basically I wanted to try to document all of this stuff because it took me a while to get everything up and running and going. But the top level README kind of tells about the environment we're looking at. I'm running PlatformIO IDE, PlatformIO on Linux instead of the Arduino IDE. Also using Segger's J-Link EDU debug device. Well, Segger J-Link, the professional version, runs, I don't know, somewhere in the neighborhood, maybe $400 to $500 for this little unit. EDU version, let me scroll down here a little bit. This is the one I'm using here. The EDU version is intended for education use only. So it's not to be used for professional use. So me as a hobbyist, I do not have a professional product, never will have a professional product. So I can purchase this, I think it was like $60 from one of the vendors. I had some ST boards, ST development boards that have the ability to configure them as an ST link rather than a J-Link. These are two different debugging protocols as I understand it. And I'm a newbie here. So, but those two boards I had blew up. Something went wrong with them and I couldn't use them anymore. So I went ahead and ordered this puppy, which I'm kind of glad I did. So it's a debug device, connects up to your USB port and also connects up to the SWD single wire debug port on your development board. That's typically a 3-wire. You've got a ground, a clock, and a data in and out transmit line. And basically what that will do is allows you to set breakpoints, if assuming you have an IDE that allows you to set breakpoints, or you're running GDB, the GNU debugger, to set breakpoints. But it allows you to set breakpoints within your device application. With generic Arduino, I've not kept up with it, but in the past, Arduino IDE, you couldn't set breakpoints. So if you're going to debug, you're limited to print statements. With this puppy, you can set true breakpoints. You can step through your device code, just like as if you were developing an application on your desktop. So that's the little gizmo that lets me set breakpoints and also allows us to do a little bit of performance investigation. To do that performance investigation, we're going to fire up Segger's SystemView. What that will allow us to do, it'll allow us to take a look at some timings of our various tasks that we'll talk about that in a bit. My end device, my edge node device is a RAK Wireless WisBlock. And we will be connecting to the Helium LoRaWan network. What needs to happen here with your device in order to run an RTOS is the underlying framework needs to support RTOS. The default Arduino framework does not. The framework, the runtime libraries, if you will, that WisBlock uses were developed by Adafruit, and there is built-in support for RTOS within that framework, within that set of libraries. So we're going to try and put all this together to see what we can come up with. Okay. So down below here, I've got a little suggested viewing order of these documents within here to kind of help it make sense. And if you have any questions, feel free to interject. If I'm spouting something wrong, feel free to interject.
And I do want to, before you take off here, I do want to say that You've done extensive documentation, for the Helium network as far as PlatformIO and, kind of getting up and running with WisBlock, with the cube cells, etc. And so, if anyone is reading over on docshelium.com, it's very likely that they're reading some of your guides there. So,
Well, now that you brought that up, the device guides out there are sorely in need of update, as some of the new folks coming on have found out. So if any of you out there want to give a hand to update those device quick start guides, that would definitely be appreciated. It would help the newbies out, and it would cut down on the questions on Discord too, I'm sure. So it's kind of an ongoing effort that needs to happen. And the Helium guys just don't have the bandwidth to keep up on that. As we all know, they're busy, busy, busy. So anyway, my plug for that. Who am I? Well, you don't care. I'm an old guy, been around a long time. Very subject to shiny object syndrome. There's actually a wiki page for that. It's kind of like, the old a pack rat. You see something shiny, you got to go look at it. Well, that's part of my problem here to get this little project off the ground. Is I see something new and it's like, oh, let's go look at that. I have some projects out on hackster.io. One of them that got me involved in Helium, actually, it was the IoT for Good contest that was held, I don't know, a couple of years ago now, I guess. And as part of that contest, the Helium folks gave away devices and access to the network with the idea that, okay, spin up some sensor projects. There's some really good ones out there. So if you go out on Hackster and look for IoT for Good, you'll find some good ones out there. I think the winning one was a beehive monitoring system, but there's several out there.
Yeah, and we also have that over on the docs.helium.com under community projects, under LoRaWan, somewhere around there.
So. Yeah, I think I did see it. So my pet project, I've been retired now for since 2013, I suppose. We did an early retirement for family reasons, but I needed to figure out what am I going to do next in life. And IoT was spinning up and buzzword and all that. So I thought, well, okay, I've got an RV. What can I do there? Okay, I would like a home security monitoring type system for my RV, but it cannot use Wi-Fi, because Wi-Fi is not available in the storage lots. It's very spotty in RV parks. So Wi-Fi is not really an option. We here in the Dallas area had a major hailstorm a couple of years back. We looked around the house here, everything was fine, got email a couple of days later from the RV storage lot, come look at your RVs. I get up there, hop on top of mine, look up one side, down the other, just about every RV in that lot had their vent roofs smashed out, which means water's now getting in the RV. So part of the project here is water intrusion. I need to know when water comes in through the roof, when things sinks, toilets start leaking, tanks overflow, tanks get full, and the typical temperature and fire and propane and etc. So I need a whole slew of sensors. And as far as actuators, I want to be able to turn AC and heat on and off as needed, disconnect main water supply if there's a leak or tank overflow, or maybe whenever I leave the coach, I want it to turn off so we have no mishaps while we're gone. We also want notification of events in that trailer. So I want a phone call, an email, or text, depending upon the severity and how important it is. Myself, I'm 5 minutes away from the storage lot. Other folks may be an hour away. They really don't want to have to go and check after every rainstorm that the coach is okay. Now, we do have a number of LoRa sensors out there, water leak sensors, temperature sensors, etc. But if I'm talking my coach here, I may have 4 temperature sensors, 4 tank overflows, 5 or 6 leak detectors. I do not want to have to manage all of those connecting up to the LoRa network. And quite frankly, there's no reason to. An in-coach edge node gateway should be able to manage all of that. should be able to turn off the water if a leak is detected, should be able to adjust the temperature if that's out of spec, should be able to notify the cloud if one of those things is out of spec, or give me a heartbeat. I don't want to have 25 different sensors connecting up to the cloud, just one.
And you mentioned heartbeats. I hate to interrupt here, but because Helium supports Class A devices, the heartbeat is what you can use in order to push control messages down to the edge node.
Right. From my point of view, the heartbeat would be probably that. I might want to say, okay, we're expecting a heat wave this week. Let's crank that max temperature up a little bit so I don't get any erroneous notifications. But for my purposes, I just want to make sure that gateway is still alive and the sensors are still active and nobody's lost their battery, for instance. But you're absolutely right, Travis. Okay, development technology here. We talked about that a little bit. VS Code, which is Visual Studio Code put out by Microsoft, has a extension, PlatformIO, which is a multi-platform development environment. It supports, well, we get into that a little bit later on. It's an easy way to onboard your device, your embedded device. It supports many, many embedded devices, supports several different runtimes. Some devices may only have a single Arduino runtime, for instance. Other devices may support Arduino runtime and embed runtime and even other runtimes. So it's just a very simple way of getting started with your device. All you have to do is define a new device within PlatformIO. If it's supported and if it has the runtime, Arduino runtime that you want, for instance, all you have to do is create the configuration and you can build it. It'll create a dummy file, dummy startup file, dummy main file. And from the get-go, you can say build, and it will pull in all of the dependency libraries for you. There's no more going out to Arduino's library manager or boards manager and pulling in the appropriate pieces and parts. PlatformIO will do that automatically for you. So it has a lot of capability that we're not going to go into today. So my little project uses a framework called mysensors.org. So I've got several sensors. I've got temperature, I've got leakage, I've got tank overflow. Those sensors need to communicate back to the in-coach gateway somehow. So rather than rolling my own communications protocol, mysensors.org is an open source community focusing on the do-it-yourself home automation. And so they have 3 or 4 different radio technologies built into this framework. There's the NRF 2401 radio, the NRF 51822 and 52844, I think it is. So there's several different radios, some of which we have here on this line here, that it supports. So what I can do is I can create a custom circuit board, pop a radio on there, connect up my sensors to it. So I may have a module that is hooked up to my temperature sensor, for instance. And my NRF module, I create my own sensor code, the code that's going to read those sensors. It's going to determine if they're over or under thresholds. If they are, then I will send a message off to the gateway. That's code I have to develop using the mysensors.org framework. It communicates via 2.4 gigahertz frequency. The WisBlock supports BLE, which is 2.4 gigahertz frequency. So it's got the frequency that we need. But the framework, this MySensors framework, does not use the BLE stack. It only uses the frequency, the radio, if you will. and I think it's a proprietary transmission protocol. This is all open source. But that framework does not support a LoRaWan interface. So I've had to create an interface to LoRaWan. It supports multiple cloud controller platforms. These are home automation platforms. They're much like Thingsboard and Cayenne and DataCake, for instance, for home automation systems. And we can do multiple cloud transports, Ethernet, MQTT. There's a serial interface as well. Supports multiple MCU boards, as you see down there. So my usage of this mysensors.org package, again, is I may have a dev board, an NRF board, or it could be another WisBlock board, or it could be an Arduino board. But I do have, I'm envisioning having a board maybe control 3 or 4 sensors. So I've got several of these boards within the coach, and they're all going to communicate back to my in-coach gateway. Okay, so as the first iteration of the IoT for Good contest used the ST Micro discovery board. Now that does have a LoRaWan radio, but it does not have any other radio. It's just that single radio. So I was able to get the mysensors.org sensors talking to the ST board, but I had to use a serial interface. So I had a separate serial radio that I could just dump out serial data out to the radio on the sensor boards, and they would connect up to the ST discovery board and transferring serial data across those radios. That was relatively slow and somewhat problematic to get it going. So it wasn't not an ideal situation. I did manage to get this whole project working at the very tail end for a couple of transmissions. But unfortunately, that shiny object syndrome kicked in with Thingsboard, and I spent far too much time trying to set up Thingsboard as my IoT cloud side to visualize the data I was getting. So after a bit of poking around under the covers of the WisBlock, I discovered something interesting. Whereas the ST board and a lot of the boards I had been playing with are using the typical bare metal superloop, the WisBlock uses Rtos, or rather the underlying Adafruit runtime uses Rtos. And there we go, shiny object alert again, Rtos, something I've been wanting to get into ever since I went down this embedded development road. So that's kind of the overview. Any questions, comments, concerns? Good. So what's an Rtos? Okay, what we're going to look at here is free Rtos. There are several different Rtoses out there in the wild. Some of them are built for safety conscious systems like medical systems. Some of them are hardened for like military use. Free Rtos is neither out of the box. It's free to use. Go grab it and integrate it into your system and you can run with it. It is, however, not guaranteed to be safe or hardened. There are third-party companies out there that will sell you our free Rtos support that is intended for safety critical environments. So free Rtos was developed around 2013. Amazon took it over in 2017. There's a link to the free Rtos.org site. Supports approximately 35 microcontroller platforms, according to whenever that wiki was updated last. Okay, and now we're going to try and get into the video. This is a video that talks about why you might want to use an Rtos. This is a video put out on DigiKey's website. DigiKey has a really great education portal where they will They have multiple videos out on their site. They're starting a new education series almost every month. Some of that is eligible for IEEE certification or classes or whatever. I'm not an IEEE member, so I'm not sure what all goes on there. But anyway, we'll give this a shot.
A real-time operating system, or RTOS, is very much like any other operating system with a few important differences. Over the next few videos, I'd like to talk about those differences and how to get started using free RTOS. We'll go over tasks, threads, prioritization, memory management, and inter-task communication. Let's get started. An operating system is a piece of software that runs on a computer or microcontroller that accomplishes a number of important functions. First, it is in charge of scheduling background tasks and user applications. In most operating systems, dozens of background processes are executing at the same time, and you probably have several applications open on your phone or computer right now. The operating system figures out how to give slices of time to each of these processes so that everything appears to be happening concurrently. Second, it manages a number of virtual resources like files, libraries, and folders, allowing applications and processes to access them when needed. Third, they can manage or provide device drivers for your system. These drivers allow the system to read and write from an external disk, respond to keyboard and mouse input, or draw graphics on your monitor. You're probably familiar with general-purpose operating systems like Windows, Mac OS, and Linux. iOS and Android also fall into this category. Most general-purpose operating systems are designed with human interaction as the most important feature, so the scheduler is designed to prioritize such tasks. That may mean some timing deadlines can be missed or pushed back, and a little lag in responsiveness, especially if it's not really noticed by a human, is acceptable. Additionally, the scheduler is often non-deterministic, which means we can't know exactly which task will execute when and for how long. If you're making something that requires an OS and strict timing deadlines, like a medical device or engine controller, missing a deadline to, say, fire a spark plug would be catastrophic. This is where a real-time operating system, or RTOS, can save the day. Most RTOSs offer many of the same functions as general-purpose operating systems, but they are designed so that the scheduler can guarantee meeting timing deadlines on the tasks. While some RTOSs might provide high-level device drivers, you'll usually see things intended for microcontrollers, like Wi-Fi and Bluetooth stacks or simple LCD drivers. You can also find bare-bones RTOSs that provide just a scheduler. With these, you'll need to import or write your own file systems and device drivers. Note that while most RTOSs provide methods for meeting timing deadlines, that's not the only reason to use an RTOS in your project. The ability to run multiple tasks concurrently can be a lifesaver, as we'll see in a moment. If you've written programs for microcontrollers, including Arduino, you're probably familiar with this kind of structure. When your program starts, it performs some setup functions, and then it executes your tasks in a round-robin fashion inside a while-forever loop. These tasks might read from sensors, perform some calculations based on those readings, and then say display something on a gorgeous LED display. This type of simple programming architecture is known as a super loop. It's incredibly easy to implement, has very little overhead, and is great when you only need to accomplish a handful of tasks on your microcontroller. In fact, there's nothing wrong with the super loop. For the vast majority of simple microcontroller projects, you're usually better off with this type of program flow, as it saves on CPU cycles and memory, and it's much easier to debug than using an RTOS. You might even have created a couple of interrupts to break the flow of execution to handle an external event like a button push or perform some action at specific timed intervals. If you need to meet strict timing deadlines for one or two tasks, you might be better off using just interrupt service routines to accomplish those tasks with precise timing. In my experience, if you need to meet a timing deadline of less than about 1 millisecond, your best bet is an interrupt anyway. If you're trying to do something with an interval of less than a few hundred nanoseconds, you either need an incredibly fast processor or it's time to start looking at custom hardware like an FPGA. Now, the unfortunate thing about this super loop architecture is that you cannot execute tasks concurrently. If task 2 starts taking a long time and task 3 is your update display task, you'll start to experience some lag. Similarly, if you're polling for user input, like from a serial terminal, or reading a sensor, you might miss data if other tasks take too long. To fix that, we can use the concept of running multiple tasks at the same time. On a multi-core processor, this is actually physically possible. However, since many microcontrollers only have one core, the CPU time needs to be split up among the tasks. We can also give higher priority to some tasks so that they happen sooner or take more CPU time. For example, if we prioritize the user input task, users will likely experience less lag, but it might mean background tasks take longer to execute. We'll talk more about time slicing and prioritization in a future video. Note the terminology used here. A task is any piece of work we want to get done in code. A thread is a unit of CPU utilization with its own program counter and set of memory. A process is an instance of a computer program that's being executed. Usually, a process will have one or more threads used to accomplish tasks. Threads within a process will often share resources like heap memory and can pass resources to each other. You'll often find that an RTOS is capable of handling only one process, but a general-purpose OS can run many processes. Note that in FreeRTOS, the term task is used to mean something closer to a thread, and you'll often see these terms used interchangeably. Because of this, I will use the term task when referring to units of CPU utilization so that it makes sense within the FreeRTOS ecosystem. Interrupts still work within an RTOS. So long as they have a higher priority than any of the tasks, they will stop code execution for all tasks, run your interrupt service routine, and return execution to where it left off. You can have more than one interrupt, but we won't get into handling nested interrupts, which can get nasty. If you're writing code for a simple 8 or 16-bit microcontroller with 2 kilobytes of RAM, you're probably best sticking with the super loop approach and using the inexpensive controller to do only a handful of tasks. While you can get a simple scheduler to run on such a device, the memory and CPU overhead of switching tasks would not leave you with many resources left for your actual program. People have ported FreeRTOS to the Arduino Uno. It's definitely a good way to tinker around with it, but I don't know how ultimately useful it is. As you move into more and more powerful microcontrollers, it becomes much more viable to run an RTOS as you've got clock cycles and memory to spare for things like a scheduler. While you can still run a bare metal super loop on something like an ESP32, I usually find that the whole reason I bought something with that much computing power is to run several concurrent tasks. Which brings me to the ultimate question of, why would you want an RTOS? There are a number of reasons, but the best one that comes to mind is for when you need to do several things concurrently. An ESP32 is capable of handling user input, reading and writing to an SD card, controlling hardware, and crunching numbers all at the same time. The big one for something like this is the wireless stack. These libraries require large amounts of RAM and processing power. They also need to respond to events from the network in a short amount of time, which means using an RTOS can be a massive help in this case. It can help you divide up these different features into individual tasks. An RTOS can be great if you're part of a team working on a larger project. You can divide up the tasks among the team members, knowing that each one will run concurrently. There will be some overhead and debugging to make sure everything works together though. Over the next few videos, I'll go over important RTOS concepts like prioritization and resource management. We'll practice these concepts by implementing small demo projects in FreeRTOS on the ESP32. The reason I chose FreeRTOS for this series is because it's currently the most popular real-time operating system for IoT devices, as shown by this 2018 survey from the Eclipse Foundation. While Linux still reigns supreme for most of these devices, it and Windows are general-purpose operating systems, with the exception of RT Linux. You can see that the bare metal Superloop architecture is still quite popular and an acceptable solution to many problems. Free Rtos is also free and open source, making it easy for you to try out. Note that as of 2017, Amazon has taken over maintenance of the Free Rtos project. I also recommend keeping an eye on the Zephyr project, as it's a relative newcomer to the field backed by the Linux Foundation. The ESP32 is a powerful IoT microcontroller that's packed with features. Also, you can find inexpensive ESP32 development boards. Any of them should work for this series as long as they have an associated Arduino package.
All right, that's enough. That's enough of that. I hope you got something out of that. It was a little bit long-winded, but it was definitely quicker than what I could have done. Any comments, questions, concerns? Like I mentioned, the DigiKey education site is real good. It has all kinds of different things and videos going on. This guy here has a whole series, as he mentioned, videos on Rtos. There are a number of them out on YouTube that will take you step by step through Rtos and through several different videos. There's a lot of good information out there, a lot of good videos. This is just one of them. So I hope that was a pretty good introduction to what an Rtos is. It's much like a thread programming in the desktop environment. And he went through some of the things in my talking points here. Tasks can be created, self-terminated, or terminated by other tasks that can be suspended or blocked. Each task has its own private stack space, but as he mentioned, they share heap space. Okay, one thing I wanted to kind of stress here is that in this environment, when we talk RTOS, real-time operating system, real-time is not instantaneous response. That's not what it means in this environment. Rather, what they're trying to do here is guarantee that if you have a task that must run every 10 milliseconds or every 5 milliseconds, the intent here is to guarantee that that task will run within that time constraint. Not necessarily an instantaneous response to external stimuli, but that task will run as often as you want it to. That's what they mean by real time. FreeRTOS supports a couple different kinds of scheduling policy. It's generally called prioritized preemptive scheduling with time slicing. Preemptive is if I have task A is currently running and task B is a higher priority than task A, and task A has not yet completed, but he's completed his time slice that he's allowed, then task A will be preempted. It will be stopped. The register information will be saved off. Task B will be switched in. It will run its time slice or to completion, whichever comes first. If its time slice expires, then the scheduler may schedule task A to run again, or it may schedule a higher priority task to run. So the scheduler is responsible for determining how long a task can run and which task is going to run next. You can have several tasks in your system, in your environment, and each task can be given a priority. So if you've got something that needs to run periodically, regardless of what else is going on, you might want that at a higher priority. Output to the debugger, debug output may be a very low priority. You want it to come, but you don't care if it's timely or not necessarily. In my little project, I've got 2 radios that the WisBlock is working with. One radio connects up to the LoRaWan network. The other radio connects up to the MySensors.org framework with my sensor modules. So I've got 2 radios. And so I want those radios to be serviced on a very periodic schedule. I do not want my debug output, for instance, to interrupt my radio response. So this is kind of what drew me to the Rtos, was I've got a couple of tasks, my radio communication tasks, that I want to make sure that they can run and not get stalled out and miss messages. I don't want to miss a receive from the network. I don't want to miss a receive from the mysensors.org sensors. So in my mind, the Rtos is a natural fit for that. The time slicing part of this, of the prioritized preemptive scheduling, the time slicing part can be disabled within the free Rtos. If you do that, when a task runs, it will run to completion. It does not get preempted. So if you don't like the fact that Rtos preempts your task, you can set the scheduler so that once my task gets running, it's going to run to completion and nobody else is going to interrupt it. Probably not a good choice, but you might have a reason to do that. Rtoses typically support a rich set of APIs for controlling tasks. Task control API create tasks, kernel control API, notifications, a lot of different APIs that you, the developer, can use to control your tasks and to communicate, inter-task communication and inter-task control, etc. So there's a whole slew of things that you can do, and we're not going to get into most of those today, if any. Some of the more important ones are the inter-task communications. You have semaphores, mutexes, and stream buffers, and queues, to where the whole idea here is that if you need to synchronize tasks, if a task, for instance, I have a task that communicates a message to the LoRaWan network. Okay. I don't necessarily need that task to run all the time. I only need it to run when there's a message from my sensor network that needs to get forwarded up to LoRa. So in that case, I need some sort of signaling mechanism to signal my LoRaWan task that, hey, here's some data, send it on up, and the task will wake up, grab the data, send it to the network, and go back to sleep. At least that's the hope. So we can do all kinds of different communications. Maybe task B needs to wait until task A receives data from the LoRa network before it processes it and does something else to it. Well, let's have task B wait, and we'll have task A wake it up in some fashion. So you can use semaphores, which says, task B says, it's kind of like, I think when you're on the road and there's a road construction and they pass the baton from one line of cars to the other, the last car in the line gets a baton, takes it through the construction zone, hands it off to the controller guy there. He gives it to the that signals him that direction of cars can flow. And when enough cars have gone through that direction, the controller gives the baton to the last car so that he can deliver it to the control guy on the other end to say, okay, now you can send cars, and that sort of thing. This is the communication back and forth between the tasks. Rtoses, of course, are not flawless. Each task has its own stack. And when you create the task, you tell it how large of a stack you want that task to have. So just like a normal process, it's subject to overflow. Put too much data on the stack of that task and it's going to crash. Interrupt response time, again, just like with a super loop, you need to limit the time spent in interrupts. Some Rtoses, at least free Rtos, has some special APIs that need to be called when you're executing within interrupts. And typically those APIs will have an underscore ISR counterpart to it. You have priority inversion, a high priority task can in theory be blocked by a lower priority task to where it will never get a chance to run. Some Rtoses try to resolve that by dynamically adjusting priority of tasks, but That I'm not going to get into. It's a little convoluted. You can get deadlocks. If task A takes a lock that task B needs, and task A sleeps, blocks. Task B runs, takes another lock that task A needs. Well, now you have a deadlock because task B cannot get task A's lock. Task A cannot get the lock that task B has. So you could get yourself into a deadlock situation. And of course, you consume more resources, more tasks, require more stack space, requires more memory. Increased complexity, coding complexity, definitely, because now you've got some inter-task communication going on, hopefully, and that can increase complexity. So here you have a little link to an article that talks about the pros and cons of RTOS, if you want to get into it further. And the following after that is another link to handling interrupts. It's a interesting little talk or an article. Typically for interrupts in a bare metal super loop environment, you might have a global variable. The interrupt might set that global variable. Your super loop might check that global variable and act accordingly if it senses the interrupt has occurred. In a RTOS environment, what you can do is you can spin up a thread, or a task rather, put that task to sleep. Then in the interrupt, you can wake up that task and be done with it. You don't have to deal with the global. You've woken up the task, interrupt completes, and that task will then run when it's next scheduled to run. So your super loop no longer has to have knowledge of an interrupt. You don't have to have the global. That's just an interesting one I ran across not too long ago. And I've added some more places where you can learn more about RTOSs, webinars and online courses. Jacob Beningo is the first one there. He does a lot of education for embedded programmers. And he has his own company. He offers in-house education as well as does a number of the videos on the DigiKey site. And he has a playlist out there on YouTube as well. He does a really, really good job of explaining things, as does Kieran. Kieran with FastBit. He has a YouTube playlist as well, but he has several courses on Udemy, and his are real good for beginning embedded programmers. He's got several that runs through the gamut of embedded programming. They're really good. Udemy has other embedded programming courses as well as lynda.com, and YouTube, of course, has a ton of them out there. You just got to go search for them and you'll find several people that do multiple videos from start to finish, from beginning on up to more complex. So that's kind of all I have about RTOS. Okay, I talked about earlier about using the Segger J-Link debug module, and this here little README kind of talks about that. So if you're interested in trying to set all of this up, I'm hoping all of this information here is fairly complete. If not, feel free to ping me. I'm Leroy LE on Discord. The Segger Debug J-Link module has a configurable upload speed, communication speed. That communication speed for an EDU module is limited to 30 kilohertz, I think it is, or megahertz. I think it's kilohertz. Anyway, it's limited to 30,000. The production modules, the $400 to $500 modules, can go much faster. And what you'll find is out of the box, you may have some communication issues because it's not able to, the EDU version is not able to keep up with the sheer amount of data. But the professional version can go up, I think, 50,000 hertz or kilohertz or something like that. It's much faster, in other words. But it's important in this environment. You have three things to be concerned about the communication speed for this debugger module. You have the debugger module itself. You have PlatformIO when it uploads and debugs code, uploads code via that debug module to your device. And when you debug to your device, the PlatformIO has a communication speed that you need to set. And SystemView, that we'll take a look at here in a bit, also has a configurable communication speed. All of those need to be consistent. They need to be the same. At least that's what I have found. I had a lot of trouble with buffer overflows reported out of SystemView, which says you can't process the data fast enough, until I got all three of those in sync. Then it settled down some. Then I discovered my Linux did not have enough swap space. Once I fixed that, things settled down immensely. So this is kind of an important thing, at least the communication speed, that is consistent across the three items that are going to use that debug device. Another note here is that Segger has developed some software to make the ST-Link debug modules put out by STMicro somewhat J-Link compatible. I do not know if running this conversion process will allow you to use SystemView and use some of the Rtos configurations here that we're going to talk about here. I don't know that one way or the other. It's possible, it could, I just don't know. I throw it out there as that's a possibility. If you have an ST development board and don't want to go purchase the J-Link board. Okay, so this is kind of all about Segger. Then we start to get into SystemView. And SystemView is used to analyze your runtime. It's a continuous recording of what's going on in your system. In order to use SystemView, your APIs that you're calling must be instrumented. In other words, you've got to have a call that says, hey, I'm entering this API, now I'm leaving this API. It's got to be instrumented in order for you to have a visual indication of what's going on. The beauty of FreeRTOS, at least within the Adafruit implementation, is that it's all in there. It's all baked in. All you need to do is enable it via a compiler flag. Now, when I say it's baked in, the RTOS API functions are instrumented. Your custom API functions, of course, are not. The other remaining Adafruit API are not instrumented. So what you're going to see is only RTOS calls, task start, task running, task idle, task completion, that sort of thing. You can add instrumentation to your own APIs or to the other runtime APIs. Segger does allow that. There are SystemView API that you can call, sprinkle within your code to get a better look at what it's doing. Unfortunately, their documentation for how to do that is not real good. And I have not found any tutorial out there that talks much about instrumenting your own code. So, and some of their documentation is very hard to follow. So it's kind of like, well, it can be done, but good luck. SystemView works on many CPUs, yada, yada. It's free for non-commercial use without limitation. I heard rumblings that there is a professional version, but I don't know what that gives you beyond the free version. And here's a link to the download page. A little talk again about the communication speed. And this tells us how to set the communication speed that I talked about earlier within SystemView. And also talks about how to enable the SystemView support within your application. And again, this is within the RTOS APIs. If you add a build flag called config sysview equal to 1, into your build flag arguments, that will enable SystemView API within the free RTOS framework. Again, not within your custom program and not within the remaining runtime, just within free RTOS. Here are some, I'll talk about this when I get to the demo. Some of the things that need to be set in your PlatformIO INI file, configuration file. This is where you configure things for PlatformIO projects. The PlatformIO PlatformIO.ini is where you define extra build flags. It's where you define what upload protocol, whether it's J-Link, ST-Link, or using the default USB debug upload protocol.
And you can set a baud rate there. Pardon my interjection as well. And so you can default to like 115.2. So you don't have to set that every time that you go into a serial monitor mode there.
Right. That's your debug output baud rate. Yes. There's a whole slew of configuration options within this PlatformIO.ini file. It's pretty interesting.
It really is, because what it's doing there is I can define all of my dependencies within that file, and it will go out and actually get those for me every time I build. And so that's one thing that a lot of people have issues with the Arduino IDE, where you have libraries that kind of step all over each other, especially with LMIC. And so this allows me not only to define and have it go out and get something for me, a library, but I can actually revision lock that to a particular version that I want it to use. So it's a very powerful functionality right there.
Right, or you can tell it, hey, just get me whatever the latest version is.
Yeah.
So if the developer updates the library, you'll grab it automatically.
Yep.
Which, like you say, can be a problem.
Yeah, right.
Okay, for SystemView, there are some things that some SystemView APIs that need to be called at startup time, when your device starts up or when your application starts up. When an application starts up within the C environment, main is called first thing. In our Arduino environment and our PlatformIO environment, if we're not running, well, even if we are running bare metal, in an Arduino environment, the main function that's running is buried deep within the Arduino libraries. And the same is true within the Adafruit implementation. The main that first gets started is buried deep within the framework Arduino Adafruit 52 cores directory. If you roll your own, there are some calls to the SystemView API that set a configuration and initialize and start the actual tracing. So you're going to have to go grab those and pop them into your main if you create a customized main startup file. And this here goes over setting up our device speed again that I talked about earlier this is for J-Link, and how to do that with some of the downloaded software that you get from Segger. One thing I sort of mentioned was the buffer overflow. If data is coming too fast, buffers can overflow. You have a buffer on your device side where the data is stored before it is transferred across the J-Link module and USB to the display system where SystemView GUI is running. I've had to bump that buffer size up in order to try to get rid of some of those buffer overflow messages. So that's kind of something to look out for. If you're running SystemView and you get a constant buffer overflow messages, this is something you'll want to take a look at. SystemView uses for interrupts, when it just shows you interrupts, it will typically show you the interrupt number. System interrupts are given a number. So SystemView has a way that you can map that number to a human readable value. And I'll show you that during the demo. But this kind of tells you how to do that mapping, some of that mapping to get from a system interrupt number to something that's human readable in the GUI. We have a thing called performance markers. This is some of the things some of the API that you can call, you can sprinkle in your application code in order to determine how long something runs. So you have a mark start, a mark stop. All that does, deposits a message in the stream of messages that comes into the SystemView GUI that says, okay, you have hit the start here, you have hit the end here, and it'll give you timing information and show you on the graph. And I've got the demo will show you some more about that. Again, this file here is all about things that you might need to do to get this up and running. These are some of the tasks that my application has. Without the aforementioned naming to human readable form, what you'll see in the UI, in the GUI, is ISR number 33, ISR number 55. Well, those don't make much sense by themselves. So I've given them, as I'll show you, names, human readable names. So we have a sysTick task. That's just a timer task. The sysTick fires off periodically based on, I think, a built-in timer. And this is kind of the guy that runs the show. The periodic timer that ticks off, that says, okay, scheduler, you need to run, or task has been running for X number of ticks, etc. You have a scheduler task. He's responsible for determining which task runs next. Is there a higher priority task available to run? Is this task now unblocked so I can move it to the run queue and make it available to run? So he schedules all of the tasks. And so these here are Rtos tasks that the Rtos system will create for you. We have a USBD task. This is the USB handler that gets called when you do debug outputs. There's another task called callback. Now these here tasks are created by the Adafruit implementation of Rtos. So the Adafruit main that we saw a little bit earlier creates these tasks, the USB handler and something called callback. I've never seen callback run. I think it has to do with BLE support, true BLE stack support, but I'm not positive. There's an idle task. The Rtos needs to be doing something at all times. Something has to run at all times. If nothing else is available to run, the idle task just sits there, runs, and marks time. We have a loop task that this is the main user loop, or what would have been the super loop. And again, this is another one that the Adafruit main starts up. This loop task is what calls your application loop function. And we have a LoRa task, and some of these tasks have defined priorities. The PRIT task has a priority of 3. Higher priority number means lower runtime priority. Priority of 0 would have absolute priority over all others. Priority 3 here says, well, if priority 0 is not running, if there's no priority 1 task or no priority 2 task, well, then we'll run the priority 3 task. So the higher the number, the lower the priority. So we have a LoRa task here, which is priority 2. This runs the radio IRQ process, and this is running RAK's LoRaWan code. When Burned put out version 2 of the RAK runtime, the SX runtime. They took away having to call this API within our main loop. Prior to version 2, it needed to be in your application's loop. So it ran each time we ran through your application's loop. You've now moved that to a separate task.
And when you say burned here, this is BG Tokyo on GitHub is who you're referring to.
Yes.
Cool.
He is the fellow that has taken upon himself to develop or maintain at least this the WisBlock portion of the runtime that does all of the LoRaWan radio work. And from what I understand, that's not his main job. He's kind of maintaining that kind of as a side job. And then I have a task called LoRa task, TSK. And that is my task that I created. Its sole purpose is to wait for messages from the sensor devices communicating via the mysensor.org framework, waiting for messages to come into the WisBlock, put in a message queue, and once they're put in that message queue by the process or task that's handling that part of the communications, then this particular task is what's tasked, if you will, to send it across the LoRaWan network. So I've started my work of breaking up my application into multiple tasks. The first part of that was to separate the code that communicates with LoRa network into its own task, giving it a higher priority than, say, dumping out debug messages, so that I do not lose that communication to the LoRa network. And then I've got another couple links here to videos that go into SystemView in a little more in depth, again with Jacob and Curran, who do really good jobs talking about about SystemView and what it can do. Any questions, concerns, issues with all that crap? It's a lot to throw in there. Oh, and we have a demo. We're going to do a demo shortly.
Nice.
Again, we're using PlatformIO as our IDE, and this is a typical PlatformIO configuration. You can have multiple configurations within your file, and PlatformIO has a way of determining which one you're going to execute, which configuration you're going to use. This has just one configuration, the default, which is what I call WisCore yada yada gateway. All right. PlatformIO has a command line interface also. So you can have multiple configurations defined within this PlatformIO INI file. And via the command line, you can say, okay, I want to run this configuration or that configuration or a different configuration. With one of my other projects, I was playing around with test-driven development and test cases and such. And so I had separate definitions in here for when I wanted to run my test cases, separate from my application code. So from the command line, I could say, well, run test case 1, run test case 2, run test case 3, etc. And it would go off, and I forget what test case environment I pulled in, but it would run the test cases, which was real nice.
You were writing like test first.
I was trying to, but I didn't have much success. It was test last.
Yeah. Okay. That's yeah.
But I was trying to incorporate the test cases, which made it real nice once I got it up and running, because I could make a change and run the test suite and not have to go in and actually fire up a connection and run various iterations of sensor data.
Yeah.
So, but I haven't done that with this project. It takes time to set it up, but it's a godsend if you're in there fixing bugs. to be able to just run a test suite and know that, hey, most of the stuff still works. In this configuration for my WisBlock platform, this is the platform that PlatformIO knows it as. And when you create a new project, you tell it which platform. You go out there and you select that puppy. And well, I think it's actually board that you select. I think it's the board. And part of the configuration that Bernd has set up and company, whoever set this up, fills in the rest of this. So you really only have to select board and the framework. And PlatformIO's setup configuration files within PlatformIO adds the appropriate platform. And here are some of the things that PlatformIO supports: a build type of debug versus production debug. We'll build it with debug code. These are some of the defines that I have that I'm using. Build flags is where you define your own flags. So I'm saying, okay, compile with -G, include, define these includes, these defines. Here's a linker flag that says, give me an output map. It's basically the same kind of things you would pass to GCC, or the linker for GCC would be done via the build flags. We have a thing called lib depths. And this is what Travis was talking about earlier, to where you can tell it specifically what libraries you want to pull in, the specific versions of those libraries. And in this case, it's going to deposit these libraries in a project specific directory, not a global directory. So you could have a project that says, I don't care what version of my sensors or BG's library I use. I'm going to use the global version that's stored out in platformio/framework, I think it is. And there's a couple other directories out there where global libraries are stored. This particular define here says, I want these local to this project only. Now, the ones that I've added to this project specifically for J-Link is upload protocol and debug protocol and debug speed. Upload protocol says I'm going to use J-Link to upload code to my device. Again, you can use ST-Link, or for this particular device and the STM device, if you leave that out entirely, it will use the USB port and the device's onboard upload debug support thingy jobber functionality to load your code. So you do not need a J-Link or an ST-Link in order to upload code to your WisBlock. And you folks have discovered that more than likely. Some devices out there, you do need something, an ST-Link, a J-Link, or some other device, debug device in order to load your code. I think maybe, I'm not sure if the Heltec, one of the Heltec devices might fall into that category. Okay, so we have our J-Link for the debug tool and our debug speed. This is the speed that PlatformIO, or rather the GDB server, I think that PlatformIO spins up, speed that it connects to the device. Defining a debug tool of J-Link I think that's the one that does it. When we use this setup here, we're using a GNU debugger server that ST-Link provides. And that has knowledge of Rtos tasks, or it can be, Rtos task knowledge can be enabled. And we'll see that in a bit here. Oh yes, to enable Rtos task support in the debugger, there's a couple of files that need to be changed. And this one here is one that fires up that GDB server. So it needs an extra option passed to it in order to enable task support. And this is something I'll show you. So what we're going to do, I have two situations here with my application. I've got my LoRa task. That's the one that sends messages to the network, to the LoRa network. That one has a while loop, and we'll talk about that once we get into it. It's kind of a runaway while loop. It runs all the time. So what I want to try and demo here is how we can better our performance of our application. Okay. And I list out the gotchas I talked about earlier, the communication speed, the buffer overflow, and my need for increasing swap space on my Linux platform. So let's see if we can get into our demo here. Okay, so here's our PlatformIO. So let's fire up SystemView to start with. And you're going to get this here message, non-commercial use license. You're going to get this each time you start up SystemView because it's a free product. And you're going to see something like this each time that the J-Link Debugger module is used. In other words, when you upload code, you're going to see a message like this. Fortunately, there's a little checkbox here that says, show it to me only once per day, not each time I run it that day. So it's not quite as painful. So this is SystemView. By default, SystemView will load up I guess it's the last data that was saved, the last run data that was saved. So when it pops up here, you see the system information. So you have a little bit of information about the system that's running. We're calling it Adafruit Bluefruit. The OS is FreeRTOS. Device is NRF52. Here you got some more information on your system here, yada yada, et cetera, et cetera, et cetera. And I don't know what all we have here. Number of tasks, number of ISRs, and more information. So the main windows that I've been working with here are the timeline, and this is starting when you first hit go to start recording. It starts off with 0, and these are all of the messages that come in, all of the instrumentation that's happening, and you see a lot of loop. Well, when my code first starts up, it does not. The main function within the Adafruit runtime has some code to loop until the debug output terminal starts. So we're sitting there waiting for serial input. So once I start up my putty session, then that kicks loose and the rest of the system starts up. It's just a handy way to say, I don't want everything to start until I've had a chance to open up my terminal window, or in this case, open up SystemView. Once you upload your code, it will automatically start running. So this is a mechanism to keep it in a kind of a known state until I start up the terminal, and then I can let everything run.
But it's not going to require me to connect with the terminal, correct? I mean, I kind of time out on that.
You'll wait forever and a day, I think, as is. You can go comment it out.
Yeah.
I mean, it's up to you to comment it out. I'm not sure what the default is when you first get the runtime, if that waiting is enabled or not. It may not be, but I find it handy to say, I want you to stop as soon as you upload the code. You can do that with a debugger, but I'm not always running the debugger.
Right. Gotcha.
So you'll have to go into that main, and if you want it to pause, enable that while loop. If you don't want it to pause, just comment out the while loop and it'll take off. So here you see this here I talked about earlier how you can name interrupt ISR numbers. So I've gone in and named these interrupts. So we have 3 interrupts. We've got the USB interrupt, what I call USB interrupt. It's got an ID of 55 in the system, an RT real-time clock interrupt ID of 33, and a GPIO interrupt ID of 22. Now, how did I determine these? Well, I stopped in some code in SystemView that is called when these interrupts are called, and when the instrumentation for these interrupts is called. I put a breakpoint within SystemView code so that I could then look at the stack trace and see where it's coming from. And then I gave them a name associated with that stack trace. So these are our ISR tasks, sysdig task, scheduler task, the ones we talked about earlier, the USB task, callback function, timer, the LoRa task. This is the one that handles the LoRa radio, and this is our main loop. Handles all of the code. This task here runs all of the code in your loop, in your main loop. And this is my custom task that handles the transmission to the LoRa network. Now, what you can do here is, if this loaded correctly, I can click on this arrow here, and it should go to the very first instance of that task. So for instance, if I take my timeline all the way back here and go to my first instance of my loop, well, I'm not going to get very far because loop runs all the time. Each time you click on this arrow, it goes to the next instance, the next time that task was started. Okay. So we can go to my transmission task. This is the task where I'm transmitting code to the network. And I'll run a live demo of this as well, that you can see. You can take a look at some timings. How long did it take that task to run? That's the loop. Well, I'll go back to the start here. Okay. How long did it take that task to run? And we can expand it out or contract the view. This is running a long time. This particular trace has a problem in my LoRa task in that I'm running it an awful long time, a lot. I'm transmitting data periodically, but this is far, far too much. I shouldn't be having that much activity in my LoRa task. It's only intended to transmit data to the network. And then we should have some kind of a correlation between this task and the actual LoRa task up here. This is the one that runs the RAK wireless code to handle LoRa transitions. So you see, it is not running all that much, but I have a whole lot of my tasks running. Here we can see that the LoRa task, the task that's running the actual underlying LoRa transmission code, that task running here. Ooh, and its timer is running here for a very short period of time. Well, this here part of my custom task may be where it's actually sending to the network. Okay, but I don't know what's going on here because there's no corresponding LoRa network activity going on. So I need to investigate that, see what's going on here. So SystemView helps you do that kind of thing. It helps you, it shows you how long the tasks are running and how often they run. So you might get an, you may take a look here and like I have and said, well, this task is not supposed to be running that much. It's consuming all kinds of resources. And the same could be said for our loop task. You know, my particular loop task is probably not doing a whole lot. But as we saw in the super loop gets called all the time. Even if there's nothing for it to do, it gets called. Well, we need to solve that. We don't need to call it that often. There's techniques we can use within tasks to say, okay, loop, you pause until some other task tells you to start. So we're not constantly consuming resources. We have our idle task, which is the one that runs when nothing else goes on in the system. So you should see, unless your system is heavily loaded with a lot of work, you should see a lot of time devoted to the idle task. And we see some, but not an awful lot. There are other windows within SystemView that you can look at. CPU load, and this is part of, let me get rid of the timeline here. This is part of the documentation that's sorely missing within SystemView, is how to interpret this view here. I think as we see this, the task that's consuming most of the CPU is our loop task. And we get over into the green one, I believe, is our my LoRa task. My custom task is consuming a lot of CPU time, I think, is what this is telling me. Again, I'm not sure. The SystemView documentation is very sparse on this. So if anybody gets into this and figures that out, please do let me know. Runtime is supposed to give you an indication as well as how often your various tasks are executing. But again, this is not something I've dug into at all. So I'm not, I'm clueless. And let's see, context. Again, this is another window I don't know. So there's a lot to be learned about SystemView. I think it has a lot of capability, but I have not found a good set of tutorials that talks about each of these views and how to determine what's going on, how to analyze exactly what's going on. So what I've kind of concentrated on here as a first pass is the timeline and how long and how often my various tasks are executed.
Sure.
And primarily concentrating on my LoRa task at the moment. Now I know Bernd is doing some work he had talked about on the RAK Discord over there. He's doing some work to try to set the WisBlock into low power mode. And part of what he is trying to do, or what he is doing, is controlling the main loop. Trying to get that main loop to not constantly execute. He's got a semaphore that when the main loop hits that semaphore, it's going to wait until some other task or an interrupt says, hey, I have something for you to do. And when that synchronization happens, then the loop starts up, handles that code, comes back around, and goes back to sleep or suspends or hits the semaphore, and then pauses, it blocks, it does not run. So it does not consume CPU time until something else happens, interrupt, that says, okay, now you have something else to do. I'm going to pull in another canned version. This one here, I put some code in so that my LoRa task does not execute as often. It only executes when there's a message waiting to be delivered. So before, I should have, this here is my custom task. When you create a task, it typically is a long running task. So you put your code that you want to run inside of a while one loop. So it runs forever, or however long you want it to run. So when I first implemented my task, I had my while one loop. So that task would run whenever it got a time slice from the scheduler, which is what we saw in the first canned version. Was a lot of the LoRa task was running a lot, because it would run when it had delivered the message, it would run through the while loop and check, are there any messages? No. Okay, continue running through the while loop. Check any queued messages? No. Continue running through the while loop. Okay, over and over and over and over and over again. So what I've done is I put a synchronization mechanism in there. I've said, okay, when I start this task, suspend it. The
then
task
just- yeah,
that adds
gotcha.
data to the common message queue, once it's added the data to that queue, then wakes up this LoRa task. So the LoRa task gets a signal, says, oh, hey, I can wake up, checks the message queue, there's data to be delivered, delivers the data to the LoRa, underlying LoRa runtime transmission code, comes back around my loop and goes and suspends itself again, goes back to sleep. The main loop is running. The main loop looks for code coming in from my mysensors.org. If a piece of data to be transmitted comes in, that loop then puts it into a message queue. And that message queue is one of the synchronization mechanisms for Rtos. It's a way to pass data from one task to another.
Gotcha.
So it puts it in that queue, and then it wakes up the LoRa task. There's some code.
But it's
it
actively
up.
polling. It's polling for that data. Is what you're saying?
The main loop is polling for the data from mysensors.org.
Yeah, gotcha.
Transmitters, sensors. The main loop is polling for that data. Right now, and it needs to be fixed to not do that poll.
So
But right now, it's
I
constantly
gotcha.
polling. When data comes in to be delivered to LoRa, pops it into the message queue, notifies the task, hey, wake up, you got something to deliver. The message queue is what you could think of it as a ring buffer, first in, first out kind of a buffer. I started out creating my own ring buffer. But with the Rtos, I no longer have to create a ring buffer in order to transmit data from one piece of my section of my code to the other. The ring buffer intended to handle bursty data.
Yeah.
These MySensor org sensors, when they come online, are bursty. They send out, here's my sketch name, here's my sketch version, here's some startup data. So there's several messages that are sent from those sensors when they start up that I cannot send them across the LoRa network that fast due to the timing constraints. So they get popped into a buffer. Now, PlatformIO, at least with a J-Link version, doesn't compare, and I don't know if this is true of ST-Link and generic USB uploads or not, but I noticed when I'm using J-Link that it's going to check the content of the data that's already on the device in some fashion. I don't know if there's a checksum or what, but it determines that the current image that PlatformIO has built is the same as the image that's on the device, so it's going to skip the upload. So let's start off. We'll run a debug session. You have a little bug over here that opens up the debug view. It's like Visual Studio and Eclipse. They all have different views, different ways your IDE is set up. This little bug here says, okay, show me the debug view. One thing to note in here, and I think this changed with some version of PlatformIO, is that you can have multiple projects in your workspace, in your view of files, if you will, your workspace. You can have multiple projects. And down here tells you which project you're currently building. And if you have multiple projects, you need to click on that and select the one you want to build. Because I can have another project selected down here, and I can open up files in a second project. I can change these files all day long, and I can hit build, and it's not going to build the one I think it is. It's going to build the one selected down here.
And flash it as well.
And flash it as well. Yes. Yeah. And I think that changed at some point along the development of PlatformIO, because I swear I used to say, open up here, build, and it would build whatever file I had open here. But so when you open up the debug view, you got your little green button here, but the same thing up here. You need to make sure you select the proper project that you want to debug. So by default, when I click that green button, we get a break it main here. Now, there was a version of the WisBlock that when I started the debugger, it would spin. It wouldn't stop in main. There would be a double bar here, which says we're running, and press it to pause. And that befuddled me for the longest time until I discovered all I have to do is restart. And the second start would take me to main and stop. I don't know when that got solved and when that went away. If that went away when I updated the WisBlock firmware, or if that was a PlatformIO side of things. I don't know when that went away.
Just to show everyone real quickly, if you look under breakpoints on the left, I mean, it shows you the line number on your main CPP where that breakpoint is situated. And
right, so I can click on it and we'll go there. This is my main. This is not the process's main. The process's main is down within the runtime.
Can you explain that a little bit, what you mean by that?
Okay. When a C program starts, by default, the entry point is set to a function called main. Now, you can override that with various compiler linker flags, I believe. But by default, when you compile a program, the entry point is defaulted to a function called main. Now, the runtimes, the Arduino runtime, and which Adafruit is based on, the Arduino runtime defines that main function down inside the Arduino runtime code somewhere. Okay. When we create our application, we may call the file main.cpp, but we don't have a main function inside here. We have typically our setup and our loop, typically is what we find inside our Arduino type programs. Okay. So when
and that's what you refer to as the super loop, right?
Yes. In our application main file, which I've chosen to call main CPP, not to be confused with main startup function. In our application, we create a setup function and a loop function. This loop function is our super loop. There's code within the runtimes somewhere that constantly calls this loop function over and 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 over again. It's probably in this main here somewhere. And we can probably take a look at it, but that's not really the focus here. So this is our super loop code. Okay. The debugger by default is going to stop at the entry point defined for that application. And again, by default, the entry point is main. So the debugger by default is going to stop at main. I can go into my main CPP, start my code into my code, and I could set breakpoints. And you'll see them pop up in the breakpoint window over here.
Yeah.
Now, these devices are limited to the number of breakpoints that can be set. When I was using ST-Link as my debugger, I think I was limited to something like 3 or 4 breakpoints before the debug view window would tell me too many hardware breakpoints set.
Yeah, and another thing you got to worry about here, especially with LoRaWan radio timing, if you stop on all these breakpoints, you're kind of going to break your radio. I mean, not break it. You're going to stop communicating correctly. So
yes, exactly. So what I've done in my code here is I put some stub code in to where I can pass a pound define, and the join code that normally calls the radio layer, the join code just returns and sets a flag, hey, I've joined. My place where I call the radio layer send API, just returns back and says I've sent it. So I faked it out. Gotcha. So I can test out the rest of my system here and be able to set breakpoints and not have to worry about, can I connect to the network? Has the network responded back, et cetera, et cetera.
Gotcha.
Okay, so we have our main. So I can say continue. This is your typical breakpoint controls, continue, step over, step in, step out, restart, stop. So if I go here, say continue, now something's running. Let's go over to System View. I want to start a recording. So this is starting a live recording now. And sometimes we get this message here a lot. And I haven't quite figured out how to get rid of all of these errors that SystemView pops up. Sometimes if I don't know if it's a timing issue. You're supposed to be able to run SystemView at the same time that you run the debugger. I have not had a lot of success doing that. And I don't know if it's my Linux environment or if it's the commercial version of SystemView or the commercial version of the J-Link EDU debugger. But here we see that I've uploaded the code and started up SystemView. Yeah. And all it's running my basic tasks. It's got my interrupts and my scheduler and the tasks that the Adafruit runtime starts up and my loop. That's all it's doing. There's no radio activity going on because the code is hanging out in that Adafruit main function, just waiting for the terminal to connect.
Gotcha.
So I'll start that back up. Hopefully it'll stay running. Well, now that my application is running, we should see the extra tasks showing up here. This is the version that had a lot of, there's a lot of chattiness going on with the LoRa task. All right, so my LoRa task, the task that I created, typically when you create a task, if you want it to run a long time, you have a while loop, while one, run forever, okay? And that's kind of what our super loop does, runs forever, over and over and over and over and over again. But I don't necessarily need this task to constantly run because it's just going to hand off data from the sensors and pass it on to the network. So when there's no activity from the sensors, there's no reason for this task to run. So what I can do is call an Rtos API called vTaskSuspend. This API will suspend any task. If you pass it a null value, it will suspend the current task. It puts it on the suspend list. Any task on the suspend list is not eligible to run, therefore will not get put on the run queue and will not be run. So you can put yourself to sleep if you pass a null, or you can pass a task handle and put another task to sleep. So you could have task wars where this task puts that one to sleep and that one puts that one to sleep. So down here, let's see here, where we create the task, this is creating our transmit task, it's creating the task up above. What I want to do is I want to create a semaphore. Not sure what I'm using that for anymore. But you have an API called xTaskCreate. This is where you give it the function name of the task, of the name of the function the task is going to run, the human readable name, and this human readable name, there's an Rtos configuration item that limits the length of this name. If you want a lot longer name, you must go into the Rtos configuration file and extend that. You can. Okay. You give it the stack size for this particular task. So each task can have a different stack size depending upon its requirements. And then I don't know what that is. That's something else. Priority. Okay, you can give it a priority. What priority do you want this task to have? Do you want it to run? Do you want it to have a higher priority, run more often than your debug print task, or in my case, the task that fetches the data from the sensors, or not? Or do I want a lower priority? I probably want a lower priority here because my LoRa transmission is going to occur less often than my sensor data comes in. I don't know. You'll have to play with it. If you have each of those tasks, if they have the same priority, then your tasks are going to be time sliced. So we put some code in here to suspend this task. It's going to stay suspended until this here function. It's another file, another function. This is called when there's data to be transmitted to the LoRa network. So we come in here and we queue up the data. So this is code to add my message data to the message queue. That message queue is common to this task and my LoRa, my custom LoRa task. So right now my custom LoRa task is waiting for data to be put in the queue, but it's also suspended. So there's a couple of ways you can do this. You can have the task call the API to get data out of the queue. If there is no data in the queue, that task can wait either forever or for a timed period. So I don't necessarily have to use the suspend API. I can just call the API to get data out of the queue and let it block until something's available. Once this task adds data to the queue, the blocked one then gets unblocked and is able to read the data out of the queue. Okay. But I was playing around with the suspend API. And in order to unsuspend that task, there's a couple API calls that other tasks must call in order to notify that suspended task that it can now run. And that's what we see here. Some API here. So what I've done here on my mysensors.org processing task that processes the message from the sensor network, I've added that data to the queue, to a common message queue, and I've notified that thread, hey, wake up. So my transmission thread then comes out of this suspend, immediately starts executing this code. Says, okay, am I joined? Am I still joined to the network? Okay, if I am, then do I have a message queue? Yes. Okay, read the data out of the queue and then send it off to the network. Here is where I've added some other custom API that SystemView supports, and that's some profiling API. So I can say, I want to know how long it takes this section of code to execute.
Yes.
So
Yep.
to do that,
Yeah, nice.
I add call this API, which says mark start. Okay, start your instrumentation. And down below here somewhere, I say stop. Stop your instrumentation. So this data will show up on the graph as a mark start, mark stop. So if everything is operating like it's supposed to, which obviously it isn't, then you would be able to determine how long it took this piece of code to run. One thing PlatformIO does for you as an IDE is you can hover over this function call, go to definition, and it'll take you to the definition. One thing I wanted to show you here is out of the box, if right now I've started my application, I'm debugging, I've paused it. We know there's multiple tasks being executed. But if we go over here, look at the call stack, I only see one. If I go down here and execute info threads, which is GDB's way to say, show me all threads or tasks, I only see one. I don't see the rest of them. So what I have to do is I have to go in and customize a file. This is the file that starts up the Segger GDB server. There may be a way to do this within PlatformIO.ini with a flag, but I have not discovered how. I need to add this line. Not uncommon, it's not there by default. I need to add it. This says GDB server, I need you to be RTOS aware. And here's a configuration file for free RTOS. There are several other RTOSs that this GDB server supports. So in this subdirectory here, somewhere, I think it's in the PlatformIO platforms area. It's .platformio /frameworks/ there it is there. .platformio platforms Nordic platform.py. So we have to add this line. If we add this line and rebuild our application, stop the debugger. Stop the debugger, probably load your application. You get a J-Link error. And I don't know. Let's see. I'm not sure that's going to work because it should. My application has not changed, so it did not upload the application. But this is a startup kind of a thing. GDB server startup. So now when I go to debug, you better work. You can see this little blue line going across here. That kind of tells you it's trying to do something.
Yeah.
And I say continue. I don't think it's hitting my breakpoints anymore. Startup. I have to start my terminal. Otherwise, the application is just spinning, waiting for the terminal to start. Okay, we joined. Okay, there we hit our breakpoint in our loop. Over here in the call stack now, in addition to the one that stopped, you see the other tasks that are running. Idle task,
awesome.
Timer service, our LoRa task, the radio task, the callback task, and looky here, you can do this, do that.
Wow.
Your heart's content.
Yeah.
I don't know if I suppose you can do that. No, he's waiting there, and this task is what's he doing? No, he's over there, and he's there. And so, it really does open up a whole new world. You now see the threads, all the tasks. GDB calls them threads, but it's certainly, I was used to using Eclipse and other and Visual Studio, base Visual Studio, and when I started playing with Arduino, it's like I miss my debugging. I gotta have a debugger. It's the only way I can operate.
And so we are paused within the main loop here, right? So
let's see.
And we can continue.
Paused on breakpoint. You see right to the left here, it says pause on breakpoint. The others are paused. So I can continue. I have another breakpoint. Of course, it's going to hit that each and every time. Oh, there it's running.
Yeah.
So if I just say, okay, whatever it's doing, pause. I guess we're paused somewhere. I don't know. Pause on user request. I don't know that you can say pause this one, let the others go. Okay. Some of the more powerful IDEs, you can do that. You can say pause this. I don't know about in this environment, but in a desktop application with threads, you could say pause this thread and let the rest of them run. I don't know if that's possible within the embedded environment or not. I've not played with Kyle or some of the other for-cost IDEs that are more powerful. You can see more registers. If we do,
now this is
so cool. You can do disassembly or assembly level debugging, stepping through assembler code if if you like.
Yeah.
So I mean that's a whole another couple of days of talk about PlatformIO. So this is RTOS SystemView kind of in a nutshell. I'm not an expert. This is what I've learned over the course of looking at shiny objects. So I mean that's kind of all I have for tonight. And
especially once your projects get larger, you have to have this kind of insight into what you're developing. So
right, there are other tools similar to SystemView. There are several others out there. Percepio Tracealizer is another big one that I've seen a lot of talk about it. Sat in on a couple webinars about it.
Right?
It's a commercial, yes, it's strictly commercial. I think there's a short time license. So it's a commercial product, but I get the sense that it would take you a whole level deeper than SystemView does, but I don't know that for a fact because I've not played with it.
Yeah,
That
this is
and
rad.
the production level debugger, and you can, if you get all crazy, you can do instruction level tracing, and assuming your board supports that, and it's just on and on and on and on and on, far above my head. And
Leroy, when
beyond
you're at this
shiny
point,
objects.
I think everyone is getting a little crazy when you get to this point. I thank you so much for presenting tonight.
You're
This has
welcome.
been a fantastic presentation.
Well, I hope it was useful.
Thanks, Leroy.
Really.
Appreciate it, man.
You're welcome. And don't forget to sign up to help update quick starts.
Yeah, we got these RVs out here that sit in water, that are called boats, man. And they
Yes.
we could
Yes.
seriously use your prototype, man. So,
Yeah, I may have to get serious and go hire me some UTD students to help me out get this done.
I mean, I have no doubt that there's marina owners that would just buy a whole bunch of them and stick them in their boats and make it mandatory, and charge a slip fee for it and just make it part of the package.
Yeah,
That's the beautiful thing about marinas is you kind of make one deal with the marina, and
You
then
got it. Yeah. That goes with lots of places. I mean,
yeah, man.
storage facilities, just like he's talking about with his RV. I mean, that's great. So
yeah.
many applications, guys. It's awesome.
Yeah, unfortunately, I'm too old to entrepreneur.
Yeah, I hear you.
So
Good work.
may have to go to a hackathon and sell the idea to one of those kids. Let them make their million.
No doubt.
So anyway, it's been, like I said, it's been a ongoing 3-year project for about 8 years.
And did you drop your link to the IoT for Good, your project, in here?
Yeah, it's in one of the readmes.
Okay, cool.
In probably the overview.
Good deal. I'm gonna go eat my dinner.
All righty.
Right on.
Take
Good
care.
seeing you, man.
Yeah.
Take it easy. Good deal. And with this, I guess we've almost been going about 3 hours here. I guess with that, I will thank you, Leroy, again, sincerely for presenting tonight. That was great, man. And everyone have a great week. I will see you next week. Same bad time, same bad channel. And everyone be safe, okay? Take care.
All right. Thanks, Travis. Bye.
See ya.